Welcome to this explainer. Today we're zooming way into the absolute microscopic level of computing. I'm talking about the ones and zeros. We're going to trace exactly how those super simple digits manage to build the vibrant digital media we experience every single day, and ultimately, how we manage all of that data in storage. Let's dive right into it.
So have you ever stopped to wonder how a computer actually sees the world? I mean, as humans, we perceive colors, we hear melodies, we read words. But a computer, at its very core, it's just a vast collection of tiny electronic switches. And those switches only have two physical states. Electrical current is either flowing or it's not, on or off, high voltage or low voltage. So the fundamental problem of computer science is translation. How do we translate those abstract, invisible electrical states into something meaningful, like a high-definition photograph or your favorite song?
To figure this out, we're going to break things down into three parts. First, the language of computers. Second, translating text, sound, and images. And third, storage and data compression.
All right, let's kick things off with Section 1, the language of computers. Time to look under the hood.
The absolute foundation of this language is binary. Think of binary as the ultimate digital Lego brick. Like a single structural brick, a single bit, which is just a 1 or a 0, offers a totally simple binary state. It's essentially just a yes or no answer. But when you stack them together using strict architectural rules, those bits construct the entirety of our complex digital infrastructure. Put them in sequences, and they literally represent all digital data.
Now, when you map out these number systems side by side, it's pretty revealing. Hexadecimal, which is our base 16 system, using numbers 0 through 9 and letters A through F, becomes this absolutely crucial bridge. It takes those long, messy strings of base 2 binary and neatly compresses them into a much shorter, human-readable format. Programmers can instantly understand it, and it maps perfectly alongside the standard base 10 denary numbers that you and I use every day.
And look, hexadecimal isn't just some abstract math concept. The exact shade of blue rendering on your screen right now, that is communicated to your display using a hexadecimal color code. We also use hexadecimals to write MAC addresses, which uniquely identify specific devices on a network, and to display computer memory dumps when we're debugging errors. It's literally everywhere.
Since computers only speak binary, mathematical addition has to follow some pretty strict yet simple rules. 0 plus 0 is 0, 1 plus 0 is 1. But for 1 plus 1? Well, there is no 2 in binary, so just like hitting 10 in our standard base 10 math, you write down a 0 and carry over the 1. By just following this endless sequential chain of carrying the ones, a processor can add together massively huge numbers using nothing but simple on and off switches.
But hey, addition isn't the only trick up a computer's sleeve. To handle complex math at lightning speeds, processors use what are called logical binary shifts. A shift literally grabs a sequence of binary digits and shoves them all one position to the left or to the right. By simply shifting the bits one place to the left, the computer instantly multiplies the number by 2. Shift it to the right, and you divide it by 2. It's an incredibly elegant, super efficient mathematical manipulation.
All right, there's one more foundational math rule we need to nail down: negative numbers. How do you show a minus sign if all you've got are ones and zeros? Well, you use 2's complement. It's a brilliant structural rule. You literally just flip all the bits in a number, turning the ones to zeros and the zeros to ones, and then you add 1 to the result. This specific arrangement tells the processor to treat that binary sequence as a negative value. That's the secret that allows for full-scale subtraction and negative accounting.
Moving right along to Section 2, translating text, sound, and images.
So this brings up a massive question, right? We know we can count to 1,000,000 using those ones and zeros, and we know exactly how to add and shift them. But how on earth do we bridge the gap between a giant spreadsheet of binary numbers and actually getting a computer to play a symphony?
Well, the secret sauce here is standard encoding rules. Take text, for example. We use systems like ASCII or Unicode. Think of them as giant dictionaries where specific sequences of binary numbers are permanently assigned to characters. One sequence means the capital letter A, another means the lowercase b, and so on. That's exactly how your emails are written. For sound, we capture a physical analog sound wave from a human voice or a guitar, and we slice it up into thousands of tiny pieces every single second. We measure the amplitude, the height of the wave at each slice, and record that measurement as a binary number. When the computer plays it back, it just reads those numbers and perfectly recreates the wave.
Visuals work on a pretty similar concept, specifically through the bitmap image. And a bitmap is exactly what it sounds like, a map of bits.
It's an image created by organizing a vast grid of individual squares of color, which, as you know, we call pixels. The really cool part is how these pixels are built block by block. For a simple black and white image, 1 pixel equals exactly 1 bit, a 0 for a white square and a 1 for a black square. But for modern, super vivid photos, we dedicate way more data to each pixel, often 24 bits. That tells the computer exactly how much red, green, and blue light to mix together. And remember those hexadecimal codes we talked about earlier? That is the exact math your computer uses behind the scenes to calculate the millions of possible color combinations for every single pixel in a bitmap photograph.
All right, that brings us to Section 3, Storage and Data Compression. Let's talk physical constraints.
To really wrap your head around the sheer scale of modern data, check this out. 1,073,741,824. That is the exact number of bytes in a single gigabyte. And keep in mind, a byte is 8 bits. So when you buy a phone with 256 gigabytes of storage, you are quite literally purchasing the physical capacity to store hundreds of billions of individual microscopic ones and zeros.
Because of this massive volume, we hit physical storage limits pretty fast. Calculating a file size means going back to our Section 1 math just to figure out how many bits are required. For an image, you multiply the number of pixels across by the number of pixels down, and then multiply that by the color depth, the bits per pixel. For audio, you multiply the sample rate by the duration of the song by the bit depth. You very quickly realize that high-quality media requires an absolutely astronomical amount of ones and zeros.
And man, that presents a massive technological problem. Uncompressed files are simply too huge to stream over the internet or to store efficiently on a standard device. We have a desperate, critical need to shrink these files down, which brings us to the very elegant solution of data compression.
To fix this, computers use two main compression methods, lossy and lossless. Lossy compression, which is what we use for things like JPEG images and MP3 audio, aggressively shrinks the file size by permanently throwing away data that human eyes and ears barely even notice anyway. It's incredibly efficient, but you do lose that quality forever. Lossless compression, on the other hand, works like a clever mathematical shorthand. It reduces the file size without losing a single original bit, so the file can be perfectly reconstructed. This is absolutely vital for things like text documents, spreadsheets, or zip files, where losing even one piece of data would totally ruin the whole file.
We've traveled all the way from a single microscopic electronic switch, through the math of hexadecimal and 2's complement, right up to the compression of massively huge media files. Literally everything digitally beautiful that you experience is just a sequence of ones and zeros being interpreted at lightning speed. Which leaves us with a pretty provocative final thought. As our storage grows and our compression algorithms become even more brilliant, what are the limits of the human experience that we can encode next? Smells? Physical touch? The foundation of binary allows for infinite building blocks, and we are really just getting started. Thank you so much for joining me on this explainer. I hope it completely transformed how you look at the digital world.